In this video, I want to show you how to test the functionality of different types of logic gates. So this is the setup that I'll be using. You can see that I've got an input side. The input side is going to provide the inputs to the logic gates. And so we'll be using a dip switch and some pull-up resistors. And then for the logic portion, we'll be using a NAND gate, an OR gate, and an XOR gate. And then for the output portion, we'll be using a LED and a 330 ohm resistor. So the pull-up resistors are going to be 10K ohms, and the current limiting resistor will be 330 ohms to limit the current going through the LED and then being sunk by the logic gate. Okay, so let's get started. First off, we're going to have a dip switch here, and the bottom side of the dip switch will be connected to ground. So I'm going to have a wire going to ground, a wire going to ground here. And then the top side of the switch will be connected to the pull-up resistor, and that will go to 5 volts. So this will be my power rail, then my ground rail will be down here. And then these green wires are going to the input of the logic gate. So you can see that I have switch 1 going to pin 13 and switch 2 going to switch 1 going to pin 12, switch 2 is going to pin 13. Pin 14 is tied to VCC, which is 5 volts, and pin 7 is grounded. Now, one thing I need to mention here is that for this particular video, all 3 of these logic chips have the same pinout. So I'm going to be able to just replace them, and all 3 of them have pin 14 going to VCC, and they have pin 7 going to ground, and then I'm using pins 12, 13, and 11 for the output. So 12 and 13 are inputs, and 11 is the output. So if you were to look at the data sheets, so for instance, for the NAND gate, pin 14 is VCC, pin 7 is ground, 12, 13, and then 11 is the output. Same thing for the OR gate. 14 is VCC, 7 is ground, 12, 13 are the inputs, 11 is the output. For the XOR gate, pin 14 is VCC, pin 7 is ground, pin 12 and 13 are inputs, and pin 11 is an output. So that's why I'm going to be able to just switch or swap the chips out to verify the logic. So they have the same pinout. Okay, so one thing to keep in mind is that the way I have this set up, you see the on up here. So right now all these switches are off, and when they're off, that means that there's no connection. The switch is not connecting across this middle portion. So that means that the inputs are going to be pulled up to logic 1. Whenever I close the switch, it will connect the bottom part to the top part, and so then the inputs will be getting logic 0. So it might be a little counterintuitive because you see the switch and you see them down, and you want to think, maybe logic 0 is when they're down, but actually when the switches are down like this, it's actually a logic 1. And so when I close the switch positions will be up, and that will be a logic 0. So maybe a little bit different from what you're used to. But we'll see the actual voltages on the meters. The logic gate itself, again, it's just we're going to use pins 12 and 13 for input, and then pin 11 will be the output. And then for the output portion, it's just an LED. You want to have the cathode, the short side, connected to the output of the gate, and you want to have the anode, the long side, connected to this resistor, and this resistor goes to 5 volts. So what's going to happen is that whenever the gate outputs a logic 0, that's going to forward bias the LED and cause the light to turn on. So you have to kind of think of it a little differently. A logic 0, like on the switch side, down actually means logic 1. Up, when I close the switch, that will be logic 0. And then on the output side, a 0 coming out of the gate will turn on the LED, whereas a 1 coming out of the gate will turn off the LED. Okay, and so I've got I've got the power supply and down here, and that's going to be set to 5 volts, and I got 3 meters. The first meter is probing pin 12. The second meter is probing pin 13, and the third meter is probing pin 11. Okay, so I'm going to look at the actual voltage levels as well as observing the LED itself. Okay, so I hope that that is pretty clear. And so let's go ahead and start the simulation. So I'm going to start off with the NAND gate, and this is the 74HC00. I'm going to go ahead and start the simulation here. Okay. So notice that the simulation's running, and I've closed these two switches, switches 1 and 2. They're closed, they're on, which means they're connecting ground to these green wires, which are going to the logic gate inputs. So with these two switches up, this is on, which is creating logic 0s at the input. So that's why you see 0 on the input, 0 on the input, and 5 volts on the output, because this is actually a NAND gate, right? And so that's why that happens. And so with a logic 1 on the output, then the LED is not going to turn on. Okay, so if we go and look at the truth table, okay, so for the 74 NAND gate, if we have a 0, 0 for switch 1 and switch 2, okay, and then if we look at pins 12, 13, those are both 0 volts, pin 11 is 5 volts, and the LED state is off. Okay, so that's the first combination. So let's go back and change this to 0, 1. So now I've got this is closed, so I've got a 0, then I've got a 1 here, so I've got a 0, 1, so I've got 0 and 4.99 volts, and because this is a NAND gate, it's going to output a logic 1. So a 0 NANDed with a 1 is going to be a 1, which will be 5 volts, which keeps the LED off. And so you can see that here, 0, 4.99 volts, and then 5 volts is the output, and then the LED is off. Okay. Let's check the next combination. We've got 1, 0. So now the switch is open, so it's the input's being pulled up to 5 volts, and this switch is closed, so this will be 0. So I've got a 1, a 0, and that will give me a 1 output. Okay, so 4.99 volts, 0.00, 5.00, 4.99 volts, 0.00, 5.00. The output's off. All right, so let's go to the last combination, and that's going to be 1, 1. So if I open both switches, right, if I open both switches, then that's going to be a 1, 1. And so for a NAND gate, the output should be a 0. And a 0 would turn on the LED. And so it is a 0. It's actually 364 millivolts, which is well within a logic 0 range. Okay? And so a 1 and a 1, the NAND output will be a 0, which corresponds to 0 volts, which here is showing up as 364 millivolts. Okay, and so that's for the NAND gate. All right, so let's stop the simulation, and if we switch out the NAND gate and we put in the OR gate, we're just going to do the same thing. So we'll start the simulation, and then we'll set our inputs to 0, 0. So for an OR gate, 0 ORed with 0 should give us a 0 on the output, which it does, and that will turn on the LED. 0, 1 will give us a 1 on the output, which keeps the LED off. 1, 0 will give us a 1 on the output, which keeps the LED off. And 1, 1 will give us a 1 on the output, which keeps the LED off. Okay, so the only combination that's going to turn on the LED for an OR gate is if I have 0, 0. Okay, and so that shows up here. For the OR gate, a 0, 0 will turn the LED on. Okay, and the last one is the XOR gate. So let's stop the simulation, and let's switch out here. We'll put the XOR gate there, and we'll do the same thing. So 0, 0 will give us a 0 on the output, which turns on the LED. 0, 1 will give us a 1 on the output, which turns off the LED. 1, 0 will also give us a 1 on the output, which turns off the LED. And for an XOR gate, a 1, 1 will produce a 0 on the output, which will turn on the LED. And so all of those values are here. So you can see that a 0, 0 will turn on the LED. A 1, 1 will turn on the LED because it's outputting the 0 volts, which it's 364 millivolts, but it's a logic 0. For the OR gate, the only one that's going to turn on the LED is when they're both 0, because that will put out 0 volts, which will turn on the LED. And finally, for the NAND gate, a 1, 1 will turn on the LED because it will output logic 0. And so that's how you can use Tinkercad to check out different logic functions. But like I said earlier, the reason I can swap these out is they have the same pinout. So you don't assume that every logic gate is going to have the same pinout. But for these three, they happen to have the same pinout, the same power and ground connections, and so I'm able to just swap them out. So also remember, you have to provide power and ground for your IC chips, and you need a 5 volts power supply. So I'm bringing in 5 volts here to this rail, and then ground is coming to this bottom rail. Okay, and for my meters, the black lead or the negatives all go to ground, and then the red leads are going to the inputs and outputs of the logic gate on the IC. So I think that's about it. Hopefully this is helpful, and just kind of understanding that, you know, when the switch is closed, when it's on, oops, when the switch is on, it's actually closing, making a connection, and it's connecting ground to this side, to these green wires. And when the switch is off, these green wires are being pulled up to 5 volts by the pull-up resistor. And then on the output side, when the output is a 0, because the other side of the LED is connected to 5 volts, when this side the output is 0, then it's going to turn on the LED. And then when it's a 1, it'll keep the LED off. Okay, so that will finish up this video, and hopefully it has been helpful.